really excited to be here to talk to you today about some work that I did with Michael Lacasto, and we went in search of shotgun parsers. So a very brief overview of what I'll be covering. We'll look at some context surrounding this problem. We'll actually go through our proposed definition for a shotgun parser. We'll take a look at an application of one part of that definition to Android apps, and then take a look at a couple of other software systems and see how that definition can be applied. So what are we actually looking for when we say we're going to look for shotgun parsers? The concept of the shotgun parser anti-pattern is, I'm sure, very familiar to most in this audience, and Sergey and Meredith have a couple of excellent talks about this concept, which you should all watch on the LangSec website if you haven't seen them already. But basically what we're talking about with this anti-pattern is the case where you're intermixing the use and validation of input data. This would be, of course, in contrast to the good practice case where immediately upon receiving input, you validate it with a formal grammar, read it into some native strongly typed data structure, and henceforth never actually deal with raw, untrusted input. So this is well and good, and we all colloquially understand what it means to say we have a shotgun parser. But if we want to start actually building automated tools to detect this anti-pattern, we need a stricter definition. And so this is part of what we set out to achieve. And we frame our definition in the context of static taint analysis of control flow graphs. So I'd now like to present to you informally our three hallmarks of the shotgun parser. First being large spread relative to size. So when that untrusted data enters your code, how far does it actually propagate? Secondly, the use before full recognition property, obviously, is that input data being validated before the first time that you use it? And secondly, the large number of variables involved in each tainted path. So how many pieces of program state are being affected by properties 1 and 2? And now I'd like to get into a bit more detail about each of these properties, starting with spread relative to size. So if we consider some application A, which reads in a set of untrusted inputs n, then let G be the static control flow graph which describes A, and let P sub n be the connected subgraph induced by the vertices of G that have been tainted by n. And finally, let S be the set of all such taint-induced subgraphs on G. So now with this definition in hand, we can start to pick up a few shotgun parser indicators. First, we can take a look at the diameter of that induced subgraph as compared to the diameter of the overall graph G. If you have comparable diameters, this indicates your untrusted input is spreading throughout your application. It's not being handled in a principled manner. Secondly, we can look at the cardinality of that set S. If S contains a large number of elements, this could be evidence that you in fact have multiple instances of shotgun parsers in your application. Now, coming to the second property, which is arguably the most important, the use before full recognition. Of course, unfortunately, this is also the hardest property to characterize in an automated fashion. Because, of course, if you have an input language which at all approaches Turing completeness and complexity, it becomes impossible to actually quantify whether arbitrary input into an arbitrary piece of code is fully recognized, because that reduces to the halting problem. So what we can instead start to do is to define a set of standards for handling specific, well-known, well-understood data types. So for example, we can conceive of this very simple model in which we have a single process A responsible for writing external data to an input buffer. We consider another process B, whose job it is to read data out of that buffer, perform some operation, and write to our validated buffer. Now within this very simple framework, we can start to define rules. So for example, if we have some object of type O, which is well understood, we know all about its properties, we define the rule that to fully recognize O, you need to do 5 reads of 4 bytes each, then write out 20 bytes in a specific order. And we can capture read-write memory events in order to ascertain whether this has happened. So in this way, we can start to sort of build up a whitelist, if you will, of appropriate read-write patterns corresponding to various common data types. And now we get to this auxiliary property of number of tainted input variables. So consider again our tainted subgraph, P sub n. And now let's let P sub n be a weighted graph, where the weight of each edge corresponds to the number of pieces of state that have been tainted by n after traversing node x. And again, here we can pick up a few shotgun parser indicators. So if the number of pieces of tainted state is large compared to the total number of pieces of overall state, this indicates that perhaps the prevalence of untrusted data is affecting a greater proportion of your program state. And we can also use this to start to triage areas of large, very complex control flow graphs in terms of where we want to focus further analysis. If we have a particular node after which the edge weight increases significantly, the statements or methods involved in that node are something that we'll want to focus further analysis on. And so now we can use our 3 parts of our definition to visualize this 3D definition cube. And within this space, we can talk about how prevalent each of these properties is in a given application. So of course, our pathological shotgun parser would be out here at the extremities because it exhibits all 3 of these properties in abundance. I'll now take you through a case study that we did applying part of this definition to Android apps. And our goals in this part of the study were to really establish the foundations for a full shotgun parser recognizer and to start taking a look at hopefully a different class of errors through the LangSec lens. Now, for reasons of computational tractability, we focused in this phase exclusively on the first part of our definition, namely the spread relative to size property. So again, our approach was based on static taint analysis of statement-level control flow graphs. And what we wanted to do was compute the actual path length associated with each source of taint into a given application. And our analysis used the Gimple intermediate representation, which is a representation that sits between Dalvik bytecode and source-level Java in terms of complexity. So we built our analysis on top of FlowDroid, which is an open-source static analysis framework for Android. Now, FlowDroid's native operation is to provide the user with a set of data flows that exist between predefined sets of sources and sinks. And we, of course, wanted to take that one step further and actually track how far each piece of input state propagated within that application. And we wanted to track all tainted paths, not just those which may terminate in a sink. So we made those modifications to the FlowDroid framework and picked up a couple of other pieces of information as well, unique identifiers for each taint source, so we could actually quantify these things. And we picked up the specific API calls from which each taint originated. Very high-level overview of our implementation. Each time a taint gets propagated, our custom handler gets invoked. And what our handler does is capture the incoming data flow fact object, which is just the taint source plus some associated metadata, and also captures the set of outgoing objects from that taint propagation. So if we haven't seen a particular taint before, initialize its length to 0, add it to our working set, and pick up the source from which that input originated. And we then iterate over the outgoing set, incrementing each taint, incrementing the path length of each taint in that set. So using this workflow, we were able to analyze 56 free apps out of 12 different categories from the Google Play Store. We ran each app through our modified FlowDroid, measured the path length for each input source into that application, and we then generated a histogram of normalized path lengths for each app, where in this case we're normalizing by the graph diameter. And you can see 3 such of our graphs here. So this is kind of interesting because here we have 3 very different apps from very different categories, and yet they all display this very similar shape, this sort of inverse power log shape. And in fact, this distribution was typical of the majority of apps that we surveyed. So this is kind of interesting because we see here that there are a large number of very short paths indicating that data is read in and then used immediately without being passed on. So this is, hopefully good news. But of course, we also see these long trailing tails indicating that we do have some pieces of data which propagate 20%, 25%, 50% of the way through each control flow graph. Now, of course, the caveat here is that at this stage, we're only characterizing raw path length. We're not capturing the nature of the operations along each long path. And of course, another thing I should mention is that static analysis of real applications is time and memory intensive. And this part of the project was actually my 1-semester undergraduate research project. So we only had 3 months to conduct this analysis. And so for this reason, we were only able to characterize 56 apps. So definitely a big area for further work in this project would be to scale up our implementation to now allow us to gather more data and actually start to draw some meaningful statistical conclusions. But this is okay, because really what our tool is the foundations of what can become a full shotgun parser recognizer for Android. And it can also serve as a prioritization method for app analysis. So you'll see here the Open Comic Reader app, simple application, has 100,000 unique possible paths of execution through that control flow graph. So obviously, even in an automated sense, we need to narrow in on which of these paths we want to focus on for our further analysis. And so you'll see here that it does display that familiar power log shape, but we also have 3 clusters of very long paths, including, you'll see on the far side there, we have 2 clusters of several thousand paths which spread over 80% of the way through the graph diameter. So this is the area that we're going to want to focus on when we start to characterize the second and third shotgun parser properties. And so now I'd like to take a look at 3 other examples and see how our definition can fit in and apply in these situations. Starting with the so-called ImageTragick bug, which is the cutesy name applied to the recently disclosed vuln in ImageTragick. So the essentials of this vulnerability lay in the convert function of ImageTragick, which basically allows users to delegate functionality to external functions, but as a side effect, allows them to execute arbitrary shellcode, which is fine and good if you're a user sitting on your own machine, but very, very bad if you're using this in the context of, say, a web server. So digging into the code, you can see this is the actual location where that delegate command is invoked, and it's invoked at one of these 4 places, either via a system call or by directly forking and execing. And the astute readers among you, or those with very good eyesight, will notice that we're actually invoking something called sanitize command. So it's not just raw input, and in fact, we see up here, yes, sanitize command is the output of this sanitize delegate command function. So this is good, right? Because we're performing some sort of input sanitization. It turns out not quite. So if we dig into sanitize delegate command, you'll see that it's really just a whitelist of ASCII printable characters, which indeed will defend you against arbitrary binary, but absolutely accepts anything that is shellcode. And this is actually a really interesting case of not only an example of perhaps a shotgun parser paradigm, but also an example of another LangSec anti-pattern, namely language specification drift. Because we have here a case where the validation, where it was once appropriate, didn't evolve along with the use case of this piece of software. And to close off the ImageTragick example, I just want to show you a quick visual trace. I know the text is too small to see, but that's not the point of this slide. I want to show you a quick visual trace of all of the places that raw input is touched along the path from user input to finally executing that delegate command. So you see here, we pull in argc and argv, and then just start touching argv all over the place. A few bytes are pulled off, some check is performed, some things are converted to strings, and this proceeds through about 7 function calls before finally that command is executed. So some observations here. I mean, we obviously have evidence of a relatively long path. And you may think that 7 doesn't seem like such a long number, but of course this is 7 function calls. Every one of those functions contains several hundred lines of code. That's several thousand assembly level statements. So these are long paths. And of course that was just the direct line flow that I showed you in between input and delegate execution. That input is being used in multiple functions in different branches along that path. And this is raw input. I mean, literally, we're just taking in argv, and in fact, it gets used in 5 different functions before it's ever read into a native data structure. So we absolutely have a case of input use and validation being intermixed, and in the end, that validation mechanism is unsuitable for the task at hand. And I'd like to quickly touch on Heartbleed, which everyone knows all about and is probably tired of hearing about, but this is an interesting case in that it's fairly obviously not a shotgun parser per se, but part of our definition, namely the use before recognition, still applies. Because of course the problem here is the failure to actually validate that the length of the heartbeat packet matches the specified length. And this is where the trouble arises. So I didn't show you a trace through OpenSSL because it's not particularly interesting, but I will tell you that that input is passed through several function calls before processing, but it's not really used along the way. So we don't really have that input use and validation intermixing. However, in the end, there's an almost total lack of validation of a fairly important piece of program state. And now, finally, lest you think everything is terrible, I'd like to show you a good practice example of a case where parsing was actually done correctly. And this is the HTTP request parser in the Mongrel web server. So you'll see here from this beautiful state transition diagram that what they actually did in this parser was to define a finite state machine using the Radial compiler. And of course, you'll recall that finite state machines are fully equivalent to regular grammars. So really what's been done here is that they've defined the grammar that they expect strings in the language coming into their program to be a member of. They fully validate that input, rejecting strings outside the language. And this is a good example of the nice, fully compliant LangSec way of doing parsing. And so now we can come back to this beautiful state space cube and start to place these three examples within this context. So ImageTragick, probably good shotgun parser candidate, lots of use and validation, intermixing, long path lengths, so I'm going to place him here. The Heartbleed vulnerability, less program state involved, not really a case of use and validation intermixing, but a total lack of validation of an important piece of program state. So I'm going to place it out there on use before full recognition. And finally, our poster child for processing, Mongrel, lives close to the axis here. And you'll notice that that's actually as far as possible from our pathological shotgun parser, which would be out on the extremities of the cube. And now, finally, I'd like to leave you with a couple of brief thoughts about future work and directions that we can go with this project. So really, many roads lead from here. I mean, definitely a next step would be to sort of climb the hill of Android and implement some of the things that we did not have time to implement in this project, and also to deal with some of the platform-specific complications that we encountered. Of course, there's the opportunity as well to implement this type of automated detection in other areas of software. As we've seen in the two vulnerabilities that I showed you, there's absolutely a lot to be discovered there. There's also the issue of characterizing these input-output whitelists and starting to get a handle on how we're going to automate whether or not something has been fully recognized. And then once we have all these pieces of the puzzle in place, we can start to actually rigorously classify some existing vulnerabilities and see to what extent each of these three shotgun parser properties is represented in these vulnerabilities. And that's pretty much all I have. I just wanted to acknowledge Stephen Arst from the Secure Software Engineering Group at TU Darmstadt, who's the primary maintainer of FlowDroid and was very helpful to us during our FlowDroid modification phase. And I thank all of you for your attention. Ready for questions?